This comprehensive survey on fairness-aware recommender systems delves into the importance of enhancing fairness in recommendation scenarios, its various interpretations, and its impact on both users and item providers. It highlights the negative societal impacts caused by unfairness, such as gender discrimination in job recommendations and geographic imbalance in MOOC course recommendations. The paper provides a detailed taxonomy of fairness concepts and formulations, categorizing them into pre-processing, in-processing, and post-processing methods. It also explores the connection between fairness and other principles of trustworthy recommender systems, including explainability, robustness, privacy, and more. Furthermore, the paper discusses the significant influence of fairness-aware recommender systems on real-world industrial applications, such as e-commerce, education, and social activities. The authors emphasize that fairness is crucial for enhancing the trustworthiness of AI services, as it promotes equal opportunities and reduces biases. They introduce various datasets and evaluation metrics used in literature exploring fairness in recommender systems, which can be utilized to assess the fairness of these systems. The paper concludes by discussing promising opportunities in comprehending concepts, frameworks, the balance between accuracy and fairness, and the ties with trustworthiness, ultimately aiming to foster the development of fairness-aware recommender systems. The lifecycle of recommender systems is susceptible to biases emerging in data collection, model learning, and feedback loop phases. Fairness-aware recommender systems address these biases by incorporating various fairness expressions, including individual, group, single-sided, multi-sided, and ranking fairness. To ensure fairness, methods such as using prior knowledge for cold start systems, employing fairness constraints in the loss function, and adjusting the dynamic fairness granularity are proposed. The fairness-aware systems encompass pre-processing, in-processing, and post-processing stages. Pre-processing methods include data relabeling, resampling, and modification to mitigate biases in training datasets. In-processing methods improve fairness from a method perspective, such as regularization-based methods, causal inference-based methods, and ranking optimization-based methods. Post-processing methods treat the model as a black box and solely process the model's output results. Additionally, various fairness concepts like individual fairness, equal opportunity, causal fairness, long-term fairness, and envy-freeness fairness are discussed. These concepts consider the long-term impact of fairness interventions and ensure that each user prefers their own recommendations over those of other users. Fairness-aware methods in recommender systems aim to eliminate bias and unfairness through various techniques, including in-processing methods such as regularization, causal inference, adversarial learning, reinforcement learning, and ranking methods. Regularization-based methods employ norm-based, matrix-based, and correlation-based regularization terms to alleviate different types of bias, including user-oriented bias, popularity bias, and group bias. These regularization terms can be added to the main loss function to penalize the model for predicting unfairness. Causal inference for fairness explores the causal relationships between variables in a recommender system, utilizing techniques like inverse propensity scoring, backdoor adjustment, and counterfactual inference to mitigate unfairness. Inverse propensity scoring reweights samples to reduce the influence of biased samples without altering the causal relationship between variables. Propensity score methods, such as IPS, adjust the recommendation scores based on the propensity of users to interact with items. Backdoor adjustment methods, like DECRS, remove unfairness by blocking relationships that lead to biases. Counterfactual inference methods, including MACR, transform the real-world causal graph into a counterfactual graph to alleviate biases. Adversarial learning involves a generator and discriminator to remove sensitive attributes, as seen in FAIR-TED. Reinforcement learning, such as Zhang et al.'s fairness-constrained CMDP, models the recommendation process as a constrained Markov decision process to ensure dynamic fairness. These methods address various aspects of fairness, including exposure bias, popularity bias, and time bias, to provide more equitable recommendations. By incorporating these fairness-aware methods, recommender systems can create a more transparent and equitable recommendation process, ultimately leading to a fairer and more personalized user experience. Fairness-aware recommender systems employ various techniques to mitigate biases and ensure equitable treatment of users and items. One approach is reinforcement learning, which dynamically maintains the trade-off between accuracy and fairness, such as FairRec, which combines user preferences with system fairness. Another approach is multi-objective reinforcement learning, introducing conditional networks and modifying them according to user preferences. Ranking optimization for fairness involves employing unbiased loss functions to reduce unfairness in recommender systems. Pointwise loss, such as binary cross-entropy and mean-squared error, minimizes the difference between the calculated recommendation score and the ground truth. Pairwise loss, such as Bayesian personalized ranking, maximizes the user preference gap between observed and unobserved items. However, BPR loss can be affected by popularity bias and exposure bias, leading to unfair outcomes. The crosspairwise ranking loss, proposed by Wang et al., addresses this by using crosspairwise interactions and decomposing exposure probabilities into user-specific, item-specific propensity, and user-item relevance. Re-ranking methods, categorized into non-parametric and parametric, aim to enhance fairness in recommender systems. Non-parametric methods, such as score scaling models, convert the recommendation optimization problem into a O1 integer programming and knapsack problem, employing greedy algorithms or solvers to perform re-ranking. Parametric re-ranking methods require a learning process to improve fairness during the post-processing stage, possessing better debiasing ability and competence in enhancing equality opportunity-based fairness. Evaluation metrics for fairness-aware recommender systems include accuracy metrics, such as area under curve, precision, recall, average precision, and normalized discounted cumulative gain, as well as fairness metrics, including the Gini coefficient, which measures value inequality, and KL divergence, which computes the divergence between two distributions and measures various biases. The authors emphasize the importance of using various datasets, such as Amazon, Beauty, Opinion, Last.fm, Movie Lens, Yahoo R3, and Yelp, to detect unfairness and evaluate fairness-enhancing methods. Fairness-aware recommender systems are crucial in ensuring unbiased and equitable outcomes, adhering to principles like equal opportunity and population parity. The survey highlights various metrics and methods to evaluate fairness, including KL divergence, strictness parameters, and measures such as mean, median, variance, skew, and kurtosis. Real-world applications of fairness-aware recommender systems are discussed, including e-commerce, education, and social activities, where methods like SARnet, re-ranking, and inverse propensity weighting are used to mitigate bias. The paper also explores fairness in job and news recommendations, addressing biases such as exposure bias, user bias, and popularity bias. Fairness is a critical dimension of trustworthy recommender systems, which also encompasses explainability, robustness, and privacy. Explainability requires logically explaining the decision-making process and input-output relationships, while robustness ensures safety and reliability in handling errors or inconsistencies. Privacy demands protecting personal data and preventing unlawful discrimination. Fairness is connected to other trustworthy dimensions, as methods mitigating fairness issues can also enhance explainability. Causal inference analyzes the causes of bias, providing explanations for the decision-making process. Counterfactual reasoning promotes both explainability and fairness. Connections with robustness involve constructing antidote data to mitigate data bias, making the model more robust. Fairness is also linked to privacy, as training data may contain user-sensitive attributes that must be protected. Table 4 outlines the connections between fairness and other trustworthiness properties, including explainability, robustness, privacy, and discrimination. Various methodologies are presented, such as causal inference, data modification, regularization, re-ranking, and others. These connections are crucial in developing trustworthy recommender systems that ensure fairness, explainability, robustness, and privacy. A large-scale deployment of a fairness framework in LinkedIn Recruiter has the potential to positively impact over 630 million members. This comprehensive survey on fairness-aware recommender systems delves into the challenges and opportunities for future research. It begins by introducing fundamental concepts related to recommender systems and fairness, then explores various types of biases that cause unfairness at each stage of the system's lifecycle. The authors discuss fairness-aware recommendation methods, categorized into pre-processing, in-processing, and post-processing stages, highlighting their implications. They also introduce datasets suitable for different recommendation scenarios and emphasize the need for customized fairness concepts, general frameworks, and trade-offs between fairness and performance. The paper concludes by outlining future directions, emphasizing the importance of integrating fairness and other trustworthy properties, reducing conflicts between properties, and building credible recommender systems. It highlights the need for continuous research to ensure that these systems promote fairness and trustworthiness, enhancing user satisfaction and trust in the recommendations provided. Fairness-aware recommender systems aim to mitigate bias and ensure equitable exposure for users and items. Various techniques are employed to address fairness, including fairness-aware ranking, learning to rank, and fairness-aware matrix factorization, which consider multiple fairness notions such as demographic fairness, equal opportunity, and fairness of exposure. A crucial aspect is understanding the trade-offs between fairness and accuracy, as achieving fairness often comes at the cost of accuracy. The impact of data sampling on hyperparameter optimization in recommendation algorithms must also be considered. Metalearning can enhance fairness in recommendation by incorporating fairness constraints into the learning process, leading to more equitable outcomes. Causal reasoning can eliminate popularity bias and improve fairness. Further research is necessary to understand the interplay between fairness and other aspects like diversity and privacy, and to develop more robust evaluation metrics for fairness. A comprehensive survey of fairness-aware recommender systems highlights the importance of addressing biases such as popularity bias, item under recommendation bias, and user attention bias. Approaches to mitigate these issues include debiased candidate generation, fairness-aware tensor-based recommendation, and calibrated fast-fair federated recommendation systems. Evaluation metrics for fairness, such as the Fairness Index and the average relative change in exposure, can assess the effectiveness of algorithms. Techniques for bias mitigation include contrastive learning, context bias-aware recommendation, and popularity opportunity bias reduction. Challenges in fairness-aware recommendation include the trade-off between fairness and accuracy, and the need for more diverse and comprehensive datasets to evaluate fairness. Ethical considerations emphasize that fairness is not a one-size-fits-all concept and may vary depending on the context and goals of the recommendation system. Future research directions include dynamic fairness, fairness in sequential recommendation, and fairness in multi-stakeholder environments.